Well, here is a seemingly very difficult looking and intimidating looking integral. And we're going to evaluate this one by converting to polar coordinates, and it won't be nearly as bad as this. I don't know if you see why this would be so bad. Imagine integrating this with respect to x. Ugh, right? Probably have to use some kind of fantastic trig substitution. I don't even want to go there. But we could do it probably with enough patience, but that's not the nice way to do it. So what we're going to do instead is switch over to polar coordinates. So we first have to look at exactly what is the region described by these limits of integration. R goes from 0 to 2, or actually, sorry, y goes from 0 to 2, and x goes from y, that would be the line x equals y, to the semicircle x squared plus y squared equals 8, semicircle of radius 2 square roots of 2. So, if you were to have a look at what we're actually, the region R that's described by this, of course, R goes from 0 to, or sorry, X goes from Y rather, that's it, Y goes from 0 to 2, would describe anything above the x-axis. This part describes the line y equals x or x equals y, and that's the lower limit. And then the upper limit would be from the semicircle, this is the upper x limit, from the semicircle, which is the square root of 8 minus y squared. So the region R is this blue region right in here, right? Because x goes from y to here, so and y goes from 0 to 2, so up to here is the maximum. And so this is our region. Think about it. The top, remember, when I'm integrating with respect to x first and then with respect to y, I'm drawing stripes across this region. The outer stripe hits here. The inner part of the stripe hits at x equals y. So if I drew stripes across this, and I draw stripes all the way from y equals 0 up here to y equals 2. Maybe that was clearer than all the other mumbo jumbo. I was just kidding you, I'm not sure. Okay, back to our problem. So we got our region R, and we're going to convert this thing into polar coordinates. So if we do that, notice R equals 0 to R equals 2 square roots of 2 just describes this circle, right? And if I drew rays through the origin, the outer, it would hit the outer at 2 square roots of 2, R equals 2 square roots of 2, and the inner is at the origin. So this is our R limits. And look at our theta limits, 0 to this angle. Well, this angle would just be pi over 4. That's the line y equals x, so it's a 45-degree angle right here, so pi over 4. Theta goes from 0 to pi over 4. Now, this is R. So you might ask the very good question, then why do I have my integrand as r squared dr d theta? And if you don't understand that, then I guess you forgot temporarily that we always use r dr d theta. R dr d theta is the element representing the area of a little rectangular piece in the Riemannian sum. And so back to our problem here. This horrible looking double integral simplifies to this one in polar coordinates. This one wouldn't even intimidate a fly. So we get r cubed over 3, and r goes from 2 square roots of 2 to 0, so 2 cubed is 8, square root of 2 cubed is 2 square roots of 2, so 16/3 square root of 2. And then that is going to be evaluated, by the way, d theta, I guess. That is just a constant, so a constant times d theta, integrating that is just going to be that constant times theta. So 16 square root of 2 over 3 theta, but then that theta will be either 0 or pi over 4. When we put in pi over 4, we get 4 times the square root of 2 over 3, because the 4 here, well, the 4 in the 16 and the 4 here would then canceled out, and it'll give us 4 square root of 2 over 3 pi. I don't have a picture showing you what that is. I could do that if you really wanted me to do that. Now I'm feeling guilty since I didn't make a picture, so I will make. Picture in hand, what we have here is this cone, and 2 square roots of 2 would be, well, the cone would be about to there. That's how much of the cone we're talking about relative to the R values. So it would be, if I drew this circle sector from here to here out along the x-axis, and then the y-axis I drew a 45-degree angle, we are then finding the volume underneath this cone above the xy plane and over this sector of the cone, right? The one that's over that little tiny piece of circle there. And that volume is 4 square roots of 2 pi over 3.